So in this video, I'd like to get down to the brass tacks and actually calculate an equilibrium constant using thermodynamics. And let's look at an interesting reaction. So for instance, we can take carbon dioxide and convert it into carbon monoxide and oxygen gas. And we might want to go ahead and calculate the equilibrium constant for this at 25 degrees Celsius. So you can actually do this now with what we've done in the last video. So you might want to pause the video and have a go. Otherwise, kind of unpause it and we'll do it gradually piece by piece. All right, so how would we do something like this? So we know the equation that we need is delta G standard is minus RT natural log K. So we need to find delta G standard. So we can do that by taking twice the Gibbs energy of formation of the product, so carbon monoxide gas, and 1 times the Gibbs energy of formation of my other product, my oxygen gas. Now, because it's an element, it's going to be 0. It doesn't cost any energy or free energy to make an element from itself. We're going to subtract from reactants, so we got 2 times by the Gibbs energy formation of carbon dioxide. Okay. Got to make sure we're looking up for a gas. So we can use that to calculate delta G standard. And I get positive 514.4 kilojoules per mole. So we can certainly look at that and we can say, oh, wow, that is really unfavorable, right? That reaction is not going to proceed under standard conditions. And what that's really telling us is that there's no way at 25 degrees C we can take 2 moles of carbon dioxide at 1 atmosphere and completely convert them to 2 moles of carbon monoxide at 1 atmosphere and 1 mole of oxygen gas at 1 atmosphere. That doesn't mean the reaction won't occur at all, okay? It will occur to a very small degree by which we can calculate the equilibrium constant to express that. So let's go ahead and do that now. So we can take our equation and we can rearrange and we can show that the equilibrium constant is equal to E, so the base of the natural logarithm, to the minus delta G standard over RT. Okay, so that is E, so 2.718281, right, to the power of minus delta G standard, so 514,400 joules per mole. Okay, and you might say, well, why did you change that? Well, my gas constant is 8.3145 joules per mole Kelvin. So I got to get joules and joules, otherwise the kilojoules and joules will not cancel. It will be by a factor of 1,000 in the exponent times by the temperature. So 25 degrees C is 298.15 Kelvin. And if we do that, we can see we've got E to a very negative number. So it's going to be a very small equilibrium constant as we would expect. 6.86 times 10 to the minus 91. That is insanely small. In fact, if we did an experiment in the lab and we tried to detect these products here, what we would probably find is that there'd be no way to detect them at all. 10 to the minus 1. I mean, gosh, if you had a mole of stuff, you'd have 10 to the 23. And what we're saying is this equilibrium constant, right, is just way, way, way smaller than 1 mole or 1 over 1 mole even. So we probably wouldn't even be able to measure it in the lab. Literally, if the entire universe was made of carbon dioxide at 25 degrees C, we could probably do the calculation and find there may be a handful of molecules of CO and O2, but it's such a small amount. So that's one beauty of thermodynamics, right? I mean, if you went in the lab and you tried to measure this, you probably wouldn't get anything at all. You probably couldn't get anything to detect the carbon monoxide and the oxygen, but we can calculate using thermodynamics, and it's exceptionally tiny. So that is the power of thermodynamics for you.